Yavuz. I'm an associate professor at the University of Florida, and I'm going to talk about our tool SIFT, which is a multi-threaded extension to KLEE. So our goal in designing SIFT is to detect memory vulnerabilities and assertion failures in multi-threaded code in a fast and precise way. And SIFT achieves this by performing property-directed symbolic execution and selective thread scheduling. So it performs data flow analysis on the explored paths to identify a set of instructions, the interleaving points or context switch points. And it works in multiple steps. In the first step, we use a very conservative thread scheduling to generate the first set of interleaving points. And then in the second step, we use these interleaving points to generate additional more interesting property relevant thread schedules and so on. So it continues until, of course, it either reaches the timeout or, once it finds the failure. So one type of property we're interested in checking is memory safety. So we're interested in out of bound accesses, double freeze, use after freeze, and null pointer references. As we show in this example, we might want to know whether these type of bugs would be manifested in these code locations. So it starts by finding the interfering memory accesses on the export paths, but of course it challenges that some of these dependencies may not have been revealed yet due to untaken branches. So we use lightweight static analysis to check if certain functions of interest like memory deallocations would be reachable from such unreachable basic blocks. So SIFT supports a subset of key-thread API, and for those interfering accesses that are imposed by a lock and unlock operations, we also include these in our interleaving set so that the context switches would be feasible. And we pay special attention to pointer arithmetic induced memory accesses. So SIFT finds these bugs, memory overflow, and use after free in the simple example using the shown interleaving points. And it also reports the specific thread schedules as well as the thread state at the time of the manifestation of the bug. We implemented 3 optimizations, basically partitioning of the interleaving points. In mode 1, we put everything in one. But the idea with partitioning is that each partition is applied separately, potentially reducing the number of thread schedules we generated. So in mode single, we put every IP in a separate partition, and in mode common, we put those that access common memory objects. And we implemented SIFT on top of the KLEE symbolic execution engine by making execution state multi-threaded and implementing data flow analysis and thread scheduling in the executor. And our experiments so far show that SIFT is efficient. It can effectively find memory vulnerabilities. And we experimented with some of the path scheduling algorithms in KLEE, like random and coverage-based and depth search. Looks like mode 1, which is the most desirable one, but it's kind of expensive. We do better when we use depth search. And for mode single, it works if you just need a single context switch. Then random coverage, it works much better. And the number of steps are configurable. And thank you so much for your attention.